This is 10.2 parametric curve part 2. Right, let's look at the example here where we will convert these parametric equations into Cartesian equations. Again, the parametric equations are a set of equations for x and y, and sometimes there's condition for the parameter t. And since we're in a new world, we just cannot tell what the graph of this look like. And so we're gonna try to convert to the Cartesian equation that is equivalent to this, so we can tell what the graph look like. So look at number 1 here. I have x equals square root of t and y equal t, right? And t is actually between, actually it's greater than 0 in this case. Let's see, looking at that, I have no idea what the graph look like, but I'm going to turn it into the Cartesian equations by eliminating the parameter. So the standard techniques, again, is to solve one equation for t and use substitutions. In this case, I'm looking at the second equation, see y equal t, right? So it's pretty straightforward. The t is actually y. I can solve for t, so t is y. And then you substitute into the first equations. The first equation, we have x equals square root of t, but t is y, so you substitute in, you have square root of y. Now you see that we have the relationship between x and y. So now x equals square root of y, or when I solve for y, and you square both sides, you will have y equal x squared, right? If you square both sides, then x squared equal y, right? So you end up having this equation y equal x squared. Now I know what it looked like. Well, yeah, so y equal x squared. Now, there's one thing I got to be careful. For the y equal x squared, we know that is parabola, right? It's a parabola. But then I noticed that because the t, there's a restriction for t. Okay, so the restrictions for t has to be greater than 0. And then looking at the x here, okay, so I'm looking at the x, x equals square root of t. Now, square root of t is always positive, right? So if you're plugging any values of t, then square root of t is always positive. And that means given y equal x squared, x cannot be anything because it comes from here. X has to be greater than or equal 0. So this is equivalent to this graph where x is greater than or equal 0. So can you sketch that? Yes, I can. This is actual parabola. Let me make this a little bit longer so it looks like we have a parabola open up at the origin, right? So I can plot the points quickly here. Right, so 0, 0, we have that point. Notice that we cannot do the left-hand side. X has to be positive. So basically, you can only have 1, 1, and then 2, 1, 2, 3, 4, and 3, 9. So we only end up with a right half of the parabola. That one, right? Right, so that's example 1. Now, let's look at example 2. Example 2. We have x equal 1 plus root t, and then y equal t squared minus 4t. Once again, our standard technique to eliminate the parameter t is to isolate a t or solve for t from one equation, and you do the back substitutions. In example 2, it looked like I think it's hard to solve for t for the second equations, so why not using the first equations here, right? So I can subtract 1, and we got x minus 1 equals square root of t, right? Then we square both sides, and now I have t by itself. Okay, so we end up with x minus 1 squared equal t. Okay, and then substitute back into the second equations, right? So in the second equation, you have y equal t squared, right, minus 4 times t. Now in this particular case, your t is x minus 1 squared. So let me use the colors here. So t is x minus 1 squared, so you plug in it's x minus 1 squared here, and x minus 1 squared there. So here, square, that turn into 4th power. So after you simplify, we have y equal x minus 1 to the 4th minus 4 times x minus 1 squared. So see, that is a 4th degree polynomial. Well, I'm not going to grab that one. That bit's hard to do, but you can plug in some values to x and do so, and then graph it. So it's going to be the 4th degree polynomial. All right. Now let's look at the next 3, 4, and 5 together. Now see that 3, 4, and 5, they are different from 1 and 2, and that they involve the trig, cosine, and the sine functions. Now, when we have those things a bit different, we don't solve for so we don't solve for t directly. Now, the reason is when you do that, it's going to be ugly, right? Because if you're going to solve for t, you have to do the inverse sine, so the arc sine. So even though we successfully eliminated t using the standard techniques, you end up with some cosine of arc sine of t of x, and we still can't tell what's the graph look like from our Cartesian equations. So 3, 4, and 5 all have sine and cosine involved. So when you have that, we will be looking to use this trig identity, right? So it's kind of quick identity that we're going to use. So with which identity involve cosine and sine? The basic one, right? So we have cosine squared theta plus sine squared theta equal 1. So this will be the properties that we'll be using, because when you apply this identity, you see that it becomes just 1, and there's no more theta involved. So looking at number 3, I'm gonna do this techniques, okay? So for number 3, we have x equal 4 sine t and y equal 4 cosine t. So in order to use this technique or these identities, we need to identify, isolate the sine and the cosine. So that is, if I divide both sides by 4, I have sine of t, right? Likewise, if I divide it by 4, I have y over 4 equal cosine t. And then I'm going to square both sides. Why? Because the one side squared cosine squared. So if you square both sides, you have x squared over 16 equals sine squared t. And we divide it by square both sides, we have y squared over 16 is cosine square of t. Now, what if we add the two equations together? See, on the left side, x squared over 16 plus y squared over 16, right? X squared over 16 plus y squared over 16 equal sine squared plus cosine squared. And sine squared plus cosine squared is 1. See, now I end up with this new equation containing no parameter t. So basically I'm done. But instead, because the two have the same denominator, we'll do one more step of multiplying both sides by 16. So we're going to clean up. It becomes x squared plus y squared equals 16. And now that is our new Cartesian equation that is equivalent to the original x equal 4 sine and y equal 4 cosine t. Now from here, are you able to identify the curve? Yes, right? So that's the whole point of doing this is from here, I can tell you what's the graph look like, okay? This is a circle. We know that's a circle. Where is the center of the circle? Okay, the center at the origins. Remember this one, x minus 0, y minus 0. And what's the radius? R. This is r squared, so 4 squared 16. So the radius is 4. And because I know that, then I can easily graph the circle, right? So now I know what the graph looked like. Okay, now let's graph. It's a circle, so that one. Right, so 1, 2, 3, a bit bigger. Right, so roughly, I think roughly that's our graph. Right, so again, the center at the origins with radius 4. Okay, radius 4. All right, so that is the graph. Now, one thing, again, the difference between the one that we drew, this is a circle here, x squared plus y squared 16, and the original parametric equation is that if you grab x squared plus y squared with 16, that is a circle, and that's it. But our original parametric equation is this one where t runs from 0 to 2 pi. So the parametric equation indeed have a directions involved. So like here, supposedly when you draw a circle, where do I start, where do I stop, and which direction do we go? Okay, so in order to do that, we have to determine the orientations and the locations of the starting, the ending points. We have to go back to the basic That is the table, right? So if I go, I draw the table T, always T first, then X, then Y. Remember, it started at 0, so it got to be 0 here. And then we plug in a few values. So let's say it's a pi half, it's a pi, 3 pi over 2, or 2 pi, and then you can do the math. Right, for x is t is 0, then you have 4 side of 0, side of 0 is 0. If t is pi half, side of pi half is 1. And then when t is pi, side of pi is 0 again. At 3 pi over 2, the side is -1 and 0. Right, so for the y function is this one. I plug 0 in, I got, well, actually I got it wrong here, I forgot the 4 in front. Side of pi half is 1 times 4, so this is actually 4. And likewise with -1 times 4, so I'm supposed to have -4 there. So for the y, cosine of 0 is 1 times 4, that is 4. And then cosine of pi half, that is 0. And 3 pi over 2 is -1, so I have -4. With 3 pi over 2, cosine of 3 pi over 2 is 0, and then 4. So see, these are the points, right? 0, 4, and 4, 0, etc. T starting at 0, ending at 2 pi. So initial point is at 0, 4, where 0, 4, 0, 1, 2, 3, 4. So that is the beginning, initial points when t equals 0. And then when t is pi half, we are down to 4, actually we're at 4, 0 is here. Right, and then we got to 0, -4, and then we're back to here, and then finally at 2 pi, when t equal 2 pi, we are back to the same point at the beginning. So the orientation is obviously is clockwise. So when you're asked to describe the motions, then you would say this is the moving object. We start at the point 0, 4, move clockwise, okay, clockwise on this circle, and complete 1 revolution back to the original point 0, 4. Okay, now let's look at number 4. You look at number 4, and you should realize, you're gonna realize something. But let's gonna see the pattern very soon. For number 4, the only difference is we have 2t, like two different. The only difference is that 2t instead of t. So we have 4 side of 2t, and y equals 4 cosine of 2t. So how does it? How would that look compared to the 4 side of t? You see the same technique is done. We solve for sine, we solve for cosine, this 2t, and let's do square both sides. Let's do square both sides. And again, you can see that it doesn't change anything. It doesn't change anything because it's the identity still works no matter what I have inside here, right? You add, you have x squared over 16 plus y squared over 16. You have sine squared 2t plus cosine squared of 2t. It doesn't matter, right? Sine squared of angle, cosine squared of the same angle. It will add up to 1. and you would end up with the exact same equations as before. You see that? We have x squared plus y squared equals 16 again. We have the same circle. However, the difference is, again, the orientations and other aspect. If you draw the tables like we have done with number 3, see they'll be a bit different now, t, x, and y. Now at 0, we have plug in here, right side of 0 is 0. Now, if you're going to use the same values as before, like pi half, what do you think? Oh, well, this is going to be different now, because if you plug pi half in, 2 and pi half, so make pi, you have side of pi. The side of pi is -1, and side of, side of pi is 0 in time 4, so I still got 0. Okay, and then if you're looking at pi, now it's side of 2 pi. Side of 2 pi is 0, so it's still 0. If you look at the cosine, cosine of 0 is 1 times 4, so that is 4. When I have pi half, cosine of pi is -1, and -1 times 4, I got -4. And pi, cosine of 2 pi, same as cosine of 0, so I got 1 times 4, I got 4. And if you're looking at 2 pi, I guess that's the same 0, and that's the same as 4. Now, here's an interesting case. I guess it's an case. If you plot these graphs, it will be exactly the same. Okay, exactly the same. Now, let's look at the graph. The circle, you see, it's really the same, right? It's the same size and same radius, so it's the same. However, from the table, what I can see is when t equals 0, okay, when t equals 0, then we are at 0, 4. So that means at the beginning, the initial point, we are at this point 0, 4 doesn't change. When t equals 2 pi, the terminal point, t equals 2 pi, we are still at the point 0, 4, right? So it doesn't change. So it looks like everything's the same. However, if looking at the next values, when t is pi half, when t is pi half, we are at 0, -4. 0, -4, so we are down here. When t is pi half, 0, -4 is there. Okay. When t equal pi, we are back to the point 0, 4. Here. So t equals 0, we are at this point. T equal pi half, we are there. And then the pi back to original point already. Comparing to here, we start at t equals 0 at 0, 4. When t equal pi half, where are we? It's here. T equal pi half. And t equal pi, we are there. Okay. So again, 0 here, pi half, we are here. 0 here, pi half, we are there. And then t equal pi, we are here. T equal pi, we are back to original point. So you see that the motion now is different. the t is really the time passage, right? If it's only t go from 0 to pi half, we only complete half circle, and that complete the full circle. So if you move on to plug in more point, you're gonna see from 0 to 2 pi, the graph is actually go around once, then twice back to original circle initial points. Okay, so in terms of speed, we're talking the speed. So this moving object moves twice as fast, and that's one. So from 0 to 2 pi, it's gonna move once around the circle, and here's twice, 2 revolutions. Okay, so the effect of adding the 2 here. So you can imagine if we have 3t, so that should go around this 3 times. Okay. Now, for number 5, I'm not going to spend time on it more, but when x equals 3 cosine and 4 sine t, so what will be the difference? Okay, I can do it really quick here, just roughly. So now you have t equal what 3 cosine and 4 sine. 3 cosine and all right, so that's x equals 3 cosine and y equals 4 sine of t. Now again, we use the same technique to solve for cosine. So x over 3 is cosine of t, and you have y over 4 is sine of t. You square both sine. Now it's x squared over 9 is cosine squared. And you have y squared over 16 is sine square of t. Okay, so then you add the both sides, and you can see now we have x squared over 9 plus y squared over 16 equal, again, 1s on the other side. And so what we have now is a new equations, right? So this new equation. Now this time the denominator is not the same anymore, right? So I'm not gonna multiply anything, just leave it like this form. So you should notice that it is a what kind of graph is it? It's the ellipse this time, right? So recall this will be the ellipse, and the a squared here, remember the larger, so a squared is 16, the b squared is 9. You can solve for a and b, and the center is still at the origins, but here we end up with an ellipse. Okay, and then you plot the table like this, and then you can see which ways go. Now, one thing I'm going to tell you is the graph that we have earlier, the clockwise, right? So notice that we have the sines for x and cosine for y. If we swap with x cosine, y sine, we will end up with the orientations going counter clockwise. Okay, so you expect that we will be having an ellipse where we're gonna go counterclockwise rather than clockwise, right? Right, let's finish the 10.2.